All right, let's dive into a really fascinating paradox from the world of physics. It's a question that sounds like a riddle. How can something be accelerating if its speed never ever changes? Let's unravel this mystery together. So, at the heart of this mystery is something called uniform circular motion. I know it sounds a little bit like a textbook term, but stick with me, because it hides this really clever twist that kind of messes with how we normally think about movement. So let me ask you this directly. Picture a car, and it's driving at a perfectly steady 60 miles per hour. The needle on the speedometer doesn't move one bit. Could that car possibly be accelerating? I mean, your gut reaction is probably no way, right? Well, let's find out if our gut feeling is right. To solve this puzzle, we have to look at our first major clue, and honestly, it's the key to the whole thing. It's a detail we often just ignore in our day-to-day lives: direction. This is where the story gets really good. This brings us to a super important distinction. You see, we tend to use the words speed and velocity as if they're the same thing, but in physics, they are absolutely not. Speed is just a number. It's how fast you're going. Velocity, on the other hand, is your speed and your direction. And that little addition, the direction, changes everything. To really get this, let's imagine an athlete running at a totally constant speed. If they're on a simple rectangular track, they have to change their direction 4 times to finish one lap, right? Each one of those turns is a change in their velocity, even if their pace never changes. Okay, now let's change the track to a hexagon. Same athlete, same constant speed, but now, to stay on the path, they've got to change direction 6 times. You can see where this is going, can't you? The more sides we add to this track, an octagon, a decagon, the more often our runner has to adjust their direction. The turns get a lot smaller, but they're happening more and more frequently. So let's take this idea to its logical extreme. What happens if we just keep adding sides forever? An infinite number of sides. What shape does that track become? You got it. It becomes a perfect circle. A circle is basically a shape with an infinite number of tiny, tiny sides. And what that means is that an object moving along it is changing its direction not just at a few corners, but constantly, at every single point along the way. So let's just pause and put that together. In this thing we call uniform circular motion, the speed, the number itself, can be perfectly steady. But because the direction is always changing, the velocity is also always changing. And that right there brings us to the final piece of the puzzle, the big reveal. How does this constantly changing velocity get us back to our original question about acceleration? Here's the official definition. See, acceleration isn't just speeding up or slowing down. In physics, it's defined as any change in velocity over time. And since velocity is speed plus direction, a change in direction, even with a constant speed, still counts as a change in velocity. Okay, let's walk through the logic one last time. Step 1. In uniform circular motion, speed is constant. Check. Step 2. But the direction is continuously changing. Check. Step 3. A change in direction means a change in velocity. And step 4. Any change in velocity, by definition, is acceleration. It's a perfect chain of logic. And there it is. The paradox is solved. An object moving in a circle at a constant speed is, in fact, always accelerating, because its direction is always changing. Pretty wild, huh? But hey, don't just take my word for it. We can actually prove this with a really simple classic experiment. Just picture it. You tie a stone to a string and you start whirling it in a circle over your head. What's keeping that stone moving in a circle? It's the string, right? It's constantly pulling the stone inward, forcing it to change direction. Now, here's the question. What happens if you suddenly let go of that string? Which way does the stone go? Does it keep going in a circle for a little bit? Does it fly straight out from the center? What do you think? The stone flies off in a perfectly straight line, tangent to the circle, at the exact point you let it go. This is the perfect proof. It shows that at any given instant, the stone wanted to go in a straight line. The only reason it didn't was the force from the string, which proves its velocity was changing at every single moment. So we figured out that an object in circular motion is accelerating. Now let's just quickly look at how we can actually calculate its speed. And the good news is, it's a lot more straightforward than you might think. The formula is actually pretty simple. Speed, or v, equals 2 times pi times the radius, r, and you divide all of that by the time t.
But really, all this is saying is that speed equals the distance of one full circle, its circumference, divided by the time it takes to travel that circle. So just to quickly break that down again, v is the speed you're trying to find, r is just the radius of the circle, and t is the time it takes to make one full lap. That's it. It all boils down to that simple idea: distance divided by time.
And, this isn't just some abstract problem in a physics textbook. Uniform circular motion is literally everywhere. It describes the moon orbiting the Earth. It describes an artificial satellite zipping around our planet. Even a cyclist riding on a circular track is a perfect example.
In this quote from the source material just sums it all up perfectly. A change in velocity can be because of a change in its magnitude, that's the speed, or a change in its direction, or both. For the paradox we just solved, it was all about that change in direction.
So I'll leave you with this final thought to chew on. Can an object be moving forward while its acceleration is constantly pulling it sideways? Before diving into this, you might have said no way, but now you know the answer is a definite yes. And it's happening every single moment an object is in perfect circular motion. Thanks for digging into this with me.